Hi everyone, and welcome to today's Chemistry Daily Booster. This is number 12 in our series, and it is Advanced Information Listed Topic worthy. Now this is actually section 3.2, which is for both foundation and higher chemistry students this time, so everyone wins today. What we're going to be doing then is having a look at the whole idea of energetics. Now by that we can simplify it down to primarily endothermic and exothermic reactions. First thing to know then is, what do we mean by exo and endothermic reactions? Well, an exothermic reaction is one where the temperature of that reaction mixture will increase because the reaction itself is giving out heat to the surroundings. Two good examples here: combustion and neutralization. Endothermic, it's kind of the opposite. So in an endothermic reaction, the temperature of our reaction mixture will decrease and heat is being taken in from the surroundings. This is a bit of an overlap with the biology, and I've seen this question pop on a biology paper before, but it could come up on chemistry, asking you basically, is photosynthesis an endothermic reaction? So no, photosynthesis is endothermic. You can answer it whether it's a biology or a chemistry question, covers all. Two other reactions to be aware of that are endothermic are electrolysis and thermal decomposition. They are taking energy in from the surroundings, but they don't actually tend to have a temperature decrease. That's because the energy being taken in is used to break down substances rather than to do anything else. So, what actually happens in this chemical reaction? Well, we're transferring energy primarily. We're going to transfer energy from the surroundings first of all in order to break the bonds in the reactants so that we then got these individual atoms. We then transfer energy to the surroundings when we then form new bonds between those atoms. So energy is transferred from the surroundings to break the bonds, and energy is transferred to the surroundings when new bonds form. We can draw a special kind of diagram here to represent what happens in a reaction in terms of energy. And this is a thing called a reaction profile. So it is literally this little thing over here. Now they can ask you to draw one of these, they can ask you to sketch it. So two versions. If they're expecting you to be drawing this with any form of scale, then they will print a bit of graph paper in the actual exam booklet. If it's just a blank piece of sort of space in your answer booklet, then you don't need to use a particular scale, but you do need to have the bits in the right kind of places. So you don't have to measure it with a ruler, but you do need to make sure that your reactant and product lines are in the right place. We'll come on to exactly what we mean by that in a bit. Please note, when you are drawing these, the axes labels. So progress of the reaction on the X, and then energy on the Y-axis. If obviously it's a sketch, you don't need any numbers associated, purely energy on your Y, progress on the X, okay? If obviously you are needing a scale because they've given you a bit of graph paper, use an appropriate scale and label it with the unit, with the actual titles as well as the numbers, please. So we've got two horizontal lines that we can see. We've got one on this side just here and one on the other side just there. The one on the left is the energy in our reactants. The one on the right is the energy in the products. We then have two other key bits that we need to know. One is the change in energy between the reactants and the product, which we call the energy change. Now, they can ask you to draw this on a reaction profile. Sometimes you'll have drawn the reaction profile, other times they'll give you one and just ask you to label these. First thing, these arrows are only ever going to be vertical lines. So get your ruler out and draw this carefully. For the energy change, your arrow is going to start on the actual line for your reactants. So notice how the bottom of the arrow is on the reactant line. You are then going to extend it so that the tip of your arrow is in line with your product. Now that doesn't mean we draw some weird diagonal thing across here. Do not draw diagonals, vertical lines only, remember. So what we're actually going to be doing in this case is you need to be very careful with what we do. So sometimes it's easier just to extend this out with a little dotted line first of all, so that you can see. And it could be below, it could be above. We then use our ruler, draw a vertical line, making sure the tip of the arrow is perfectly in line with the products. Label it energy change, job done. The other one, the activation energy. Again, the bottom of this is going to start in line with our reactants, so you can extend that out using your ruler again. Bottom of the line sits perfectly in line with the reactants. A vertical line drawn with a ruler again, please, and the tip of the arrow touches the top of the curve perfectly. Please don't rush these. Don't draw weird things. The kind of things I've seen before, we've had like weird curvy arrows coming round here. Don't do that. It's not a curvy arrow. It's literally a straight line, vertical, going from the reactants to the top of the curve. You'll notice I've said this several times because I do feel like with my class anyway, no matter how many times I say it, there's still some of you that get it wrong. If there's a time to listen to me and get it right, it's now. So activation energy, quite simply, is the energy we need for a reaction to start. Hence why we're going to the top of that little curve, because that's showing us how much energy we've got to put in for the reaction to then go. Quite often this is generated by heating it, because that's going to break the bonds in all those reactants nicely. Sometimes though there are reactions where we don't have to heat it. Purely mixing the chemicals together is enough to actually exceed the activation energy. Now we need to obviously make sure that if it's an endothermic reaction, we get our reactants and our product lines the right way round. Same for exothermic. If we're talking an endothermic reaction, the reactant line is going to be below the product line. Exothermic is the opposite. The reason, because in an endothermic reaction, the energy transferred to break the bonds is more than the energy transferred when new bonds form. So that means we have a positive energy change, hence the upward arrow on the diagram there. Exothermic is the opposite here. We've got a downward arrow because it's a negative energy change. The reactants line is above the products because the energy transferred to break the bonds is less than the energy transferred when new bonds form. If they ask you to describe the process of exothermic or endothermic reactions in terms of bonds or energies in bonds, that's the kind of phrase we need to use. Energy transferred to break the bonds is less than the energy transferred when new bonds form. If obviously they tell you to use sort of some information about bonds and you don't use the word bond anywhere in your answer, clearly you're getting no marks for it. So just learn those two phrases for the different types of reaction there. We then come on to a calculation we could be asked to do. So you can be asked to work out these key bits to do with bond energies. If they're going to do this, they will give you a table of bond energies like the one on this slide here. You don't have to memorize anything, you just need to use it at the end of the day. Do note this little point in our bottom box here, that the ones that they give you in a table are mean bond energies. So when you actually calculate them, then your energy changes may vary from experimental values. And that's because this is a mean of a range of different chemicals with those same bonds in there. But what actually happens when you do the experiment could be ever so slightly different, because obviously it's not a mean anymore. So how do we do this then? If they're going to be nice, they will do parts of this for you. They could even break it down into little kind of sub sort of questions. So you'll have a part I, a part II, and then a part III. So they will lead you through it. If they're being mean, they won't. They will just give you a larger space and expect you to do the whole lot. I'd be hoping for the broken down stages. What we need to do, we need to know what bonds are present. So this is go back to the displayed formula. They're not literally just going to give you names, they will give you the chemical formulas, but not in displayed format. Okay, so you need to draw your displayed formulas first of all, which will help you just count the bonds and get them right. Step 2, count the number of each type of bond. So when we've drawn out our displayed formulas, so if we were doing methane, for example, you draw it all out like this. And if it was reacting with oxygen, there we go, and then you'd have your products on the other side, which would be carbon dioxide, and we'd have water. So you draw out your displayed formulas like this, just so you can count your bonds. Then we can count them. So if we have a look at methane, first of all, we've got 4 of the carbon to hydrogen bonds. So we have 4 carbon to hydrogen bonds. And we've got our oxygen, double bond, oxygen bond. You will need to look at how many are actually present in terms of balanced equations. So obviously if we've got 2 moles of oxygen, then you'd have to times that by 2 as well. Okay, but have a look at the exact example to get that. Once you've worked out all the bonds, look at the table and substitute the actual bond names with the energy from the table. Stick all those into your calculator, multiply the number of those bonds by the energy, add them all together, and you've got your total energy needed to break all bonds in the reactants. Same thing for your products. Add up how many of those bonds there are, substitute in, multiply it up, and then add them all together. And then to work out the energy change, it's bond breaking minus bond making. So bond breaking minus bond making, i.e. the thing you first worked out minus the thing you worked out second. A hint, if they've given you the lovely 3 parts to this, so part 1 would be the energy in your reactants, part 2, energy of products, and part 3, the energy change. If you've literally sat there and thought, I have no clue what the heck I'm doing for parts 1 or 2, you can still get the mark for part 3, because if you actually just write down any number you fancy, so if we were to write 300 in the answer space for part 1, and we were to write 100 in the answer space for part 2, and then for part 3 we literally went 300 minus 100 equals 200, you know what? They're going to be wrong, but you get this mark as what we call an error carried forward. So you're not going to be penalised for this bit because you've done the right maths, you've done reactants minus products, you just didn't have the first bits right. So you get that mark, but you won't get those. If you haven't written down numbers in parts 1 or 2, you won't get these marks. So if you don't know it, stick in any old numbers you fancy. I'd suggest easy ones, and then show the energy change, how you work it out, your correct answer. You'll at least get that last part right. Last thing to bear in mind is that the sign is important. Some will be positive, others will be negative. If it is a positive, then that means that it is an endothermic reaction. If it is a negative, then that means it is an exothermic reaction. Last thing to do for today then is head on over, have a go at our quiz. Now, obviously, if there are some bits in there that you want to have a little bit of a greater look at, spend a bit more time thinking about it, there are the videos on the main channel that you can use. I would suggest having a look at past exam papers to find some of these calculation questions to get a bit of a feel for them, see what they look like, and don't forget the little hint there on how we can get some marks even if the first bits haven't gone great for calculations. Don't forget to join us again tomorrow for our next Chemistry Daily Booster.